Let's continue. Question 19. Okay, thermocol box. Okay, we have thermocol box. Offside 30 centimeters. So here, inside the box, the ice is placed. Inside the box, ice cube is placed. Okay, so here the idea is heat has to enter the box. Then only the ice gets melted. Now heat entering the box, so we can use the heat conductivity equation. We have Q is equal to uh, Q is equal to K A into T1 minus T2, T1 minus T2 into T divided by T, where D is the thickness of the thermocol box. So that's given for 5 centimeter. We have to convert into SI unit. Then this heat is used to melt the ice. So latent heat formula we have to use Q is equal to ml. Okay, so whatever amount of heat transferred through the box is equal to the heat absorbed by the ice to melt. And area you have to take as area. There are 6 spaces, so 6 into 30 into 30 cubical box. That's why, and we have to convert into meter square, so you will get the area. Now equate these two equations so that the mass of ice melt m can be calculated. Once you get the value of m, see the question it is asked, how much amount of ice will remain there after 6 hours. So it is total 4 kilogram of ice is there. Out of that, m kilogram got melted. So 4 minus m will give you the final answer. Now, next question 20. A brass boiler has a base area of 0.15 meter square and thickness 1 centimeter. It boils water at the rate of 6 kilogram per minute. When placed on a gas stove, estimate the temperature of the part of the flame in contact with the boiler. Okay, so we can have the boiler like this. We can take, then water is taken inside the container. So here water is taken and the heat is supplied from here, from the boiler. And water boils, so temperature is 100 degrees Celsius here, and here we can take temperature T1. That is the temperature of the flame in contact with the base of the boiler. Again, we can use the same formula. We have the heat conducted through the base of the boiler, Ka into T1 minus T2. T2 is 100 degrees Celsius here, into T divided by D. D is the thickness of the boiler. Okay, the thickness, this given thickness of the boiler is 1 centimeter, the base area. And that heat is used for phase change. So Q is equal to ml. Okay, so now equate these two values so that here when you substitute values m, you have to see, okay, when you get, you will get m is equal to Ka into T1 minus T2 into T divided by D. Now this equation you can divide throughout by L, or you can cross multiply equation so that T you can take towards here. When you take T, you will get m by T. That is what given in the question, m by T. Okay, 6 kilogram per minute. 6 kilogram per minute you have to convert into kilogram per second, so that you will get a Ka into T1 minus 100 divided by T. So from this equation, you can find the temperature of the flame in contact with the base area of the boiler. T1 can be calculated. Now, question 21. Part A body with a large reflectivity is a poor emitter. So here you can see always a good absorber is a good emitter. And body with a large reflectivity means the majority of radiation falling on the body gets reflected. That means the radiation is not absorbed enough there. So naturally then what happens as the radiation is not absorbed by the body, naturally its emission capacity also will be less. Okay, so as it is a poor absorber, it is a poor emitter also. Part B, a brass tumbler feels much colder than a wooden tray on a chilly day. Okay, so if heat is lost from our body, then we feel cold condition. If heat is absorbed by the body, then we feel hot. So here, when you touch the brass tumbler, the heat transferred from your body to the tumbler because it's a conductor. So you feel cold. But when you touch the wooden tray, wood is a poor conductor of heat, so heat is not transferred from your body. It is not going out from your body, so you don't feel so. Then next part C, an optical pyrometer. Pyrometer, you have to understand that it measures the temperature with the help of radiation. Okay, it measures the amount of heat radiation, infrared radiation emitted from the body, so that its body temperature can be calculated. Is calibrated for an ideal black body radiation. Use too low a value for the temperature of a red hot iron piece in the open, but gives a correct value for the temperature when the same piece in the furnace. So here, when you take a red hot iron piece, okay, when you take the red hot iron piece, you can see the radiation is escaping in all the directions in the environment, in all the ways. So if you keep the thermometer here, optical pyrometer, you have to consider as a thermometer, okay, that can measure the temperature by observing the radiations emitted from the body. So in this case, when you use the pyrometer, then you can see the radiation is not confined. The radiation is just emitting out in all the directions. But at the same time, just imagine that the entire piece of iron is kept inside the container. Then what happens? The whole radiation emitted from this body gets confined inside this container. So that can be considered as a furnace. So all the radiation cannot escape into the surroundings. The radiations get confined in the furnace. That time you take the temperature using the pyrometer, as the whole radiation is just confined, then the pyrometer can detect the total amount of radiation present inside the furnace, so that the actual temperature can be measured. Okay, in an open condition, you can see the heat radiations will just escape, so that the pyrometer cannot measure what is the actual amount of radiation present in the red hot iron piece. Then next, an earth without its atmosphere would be inhospitably cold. Okay, so that we have discussed already in greenhouse effect. The earth atmosphere gives enough greenhouse effect, sustaining the heat energy over the surface of the earth, keeping its temperature almost same both during day and night. So if there is no greenhouse effect, if you don't have the atmosphere, then you can see nighttime temperature will be extremely low, so that earth will be earth will not be suitable, okay, for the life. Now, next part E, heating systems based on the circulation of steam are more efficient in warming a building than those based on circulation of hot water. The reason we have seen already, steam contains an additional amount of heat energy, which is equal to the latent heat of evaporation. Therefore, if you take steam and water at the same temperature, steam carries more heat energy. Next, question 22. A body cools from 80 degrees Celsius to 50 degrees Celsius in 5 minutes. Calculate the time it takes to cool from 60 degrees Celsius to 30 degrees Celsius. The temperature of the surrounding is 20 degrees Celsius. The question is from Newton's law of cooling. Remember the equation. The change in temperature dT2 divided by T2 minus T1, the temperature difference between the body and the surroundings, is equal to K by ms. The total is a constant into dt. So this is a formula you have studied. Now we can just cross multiply this equation. You will get dt2 divided by dt is equal to, so all these constant we can write as a single constant capital K into T2 minus T1. Okay, let's take this equation. Two cases are given in the question. The first case, okay, body cools from 80 degrees Celsius to 50 degrees Celsius. Therefore, dT2, the change in temperature of the body, is 30 degrees Celsius and it takes 5 minutes for the process, is equal to a constant K into the temperature difference between body and surroundings. So what we have to do to calculate the temperature difference? Because it says that body cools from 80 degrees Celsius to 50 degrees Celsius. We have to take the average temperature. The average temperature is 65 minus surrounding temperature 20. Now apply the same concept for the second situation. It cools from 30 degrees Celsius, 60 degrees Celsius to 30 degrees Celsius. Again, temperature difference dT2 is 30, and we don't know the time taken for this process, is equal to a constant K into, here also we need to find the average temperature because body temperature is given from 60 to 30. So it is 45 degrees Celsius and the surrounding temperature is same in this case also 20. So now you get two relations there. Take the ratio of the relation and find the value of T. Find the value of T. So these are the questions from the exercise of the chapter. Now, in addition to that, we have discussed the supplementary topics also in this case. And I have given 2-3 questions from the supplementary topics also. Okay, so already the solutions are given there. You can just go through these questions from the supplementary topics also. Okay, thank you.